Okay folks, so I'm going to make a sequence of videos that's going to cover the topic of how we can use matrices to help us solve systems of equations. And specifically what we're going to be looking at is what are called augmented matrices. So there's not really a definition for that. You'll see what I mean by way of an example, what an augmented matrix is. So here I've got a system of equations. I called it Dagger, and it's a system. In this case, we've got two unknown variables, and we've got two equations. Okay. As far as the matrices are concerned, we're going to have a column for each of our unknowns plus a column on the right of coefficients, and then each row is going to correspond to one of the equations we're given. So this is what we call the augmented matrix. Okay. So we have, in this case, for the x column, we'd have 3 for the first equation and 5 for the second, and minus 4 for the second, for the y variable in the first equation, and 2 for the y variable in the second. And then to sort of, we don't actually have to draw this bar, but help us remind us where that equal sign showed up in the equation. We're going to draw what we sometimes call the augmentation bar. This is what makes this an augmented matrix. And as long as I remember that this column corresponds to the coefficients of the x variables, and this column corresponds to the coefficient of the y variables, then this column here would correspond to the constant terms, which have been isolated and taken over to the other side of the equal sign. This matrix conveys as much information as this system of equations does. And it turns out that we're going to learn some matrix, what are called row operations, that are equivalent to working with these systems of equations. And this gives us a very methodical way of finding solutions to systems of equations. So what I'd like you to do is go ahead and pause the video, and then go ahead and represent this as a system of equations. So pause the video and do so. So here you can see I've taken this system of equations and represented it as its augmented matrix, and we all understand that the first column corresponds to the coefficients of the first variable, the second column corresponds to the coefficients of the second variable, etc. Notice that here, since I have no x term in this third equation, we went ahead and put a 0 to represent the coefficient in front of x there. Okay, so why are we going to be representing our systems of equations as augmented matrices? Well, let's look down at this here, and we're going to go ahead and call these two matrices equivalent matrices, which means if we were to finish doing, and I didn't put the augmentation bars on these, but if we were to finish doing the row operations on both of these in order to find the corresponding solutions, we would find that both matrix A and matrix B have the same solution. Okay. So that's equivalent, so that you should recognize that that's equivalent to saying that this system of equations right here, which is the system that goes with this matrix, and this system of equations right here, which is the system that goes with matrix B, well, you've learned in algebra classes that these are equivalent systems. And in fact, how does this work? Well, the first row of each are the same, and notice that the second row of this system is really just a multiple of this row. That is, I took all of the, I took both sides of this equation and multiplied it by 2 to come up with this equation right here. But we all know that when we solve this system of equations, we end up with the same solution set as when we solve this system. And so that's the idea here. These two matrices are equivalent matrices. And it turns out that there's a handful of operations that we can do that will result in, based upon our algebra methods for solving systems of equations, there's a handful of matrix operations that we can do that will always give us equivalent matrices. And so here I've listed them. At any point in time when you're dealing with an augmented matrix, you could interchange any two of the rows. You could swap two of the rows, and whatever the corresponding solution is of that new matrix, that will correspond to the same solution of the original. So swapping rows does not change the answer. Likewise, multiplying any of the rows by a non-zero number won't change the solutions to the augmented matrix, and that's what we see going up here. So this matrix A is representative of this system, and here matrix B is for the second. But notice I could get from this equation to this equation simply by multiplying this row by 2, and that's what we do here in the matrix form. We multiply this row by 2, we multiply the second row of matrix A by 2, and we end up with this second row in matrix B. And what we're saying here is those two matrices are equivalent, meaning they will have the same corresponding solution set. Finally, and probably the most complicated row operation and the most important one to learn, is that we can replace any row by a linear combination of that row and another row. So what do I mean by that? I mean that what I could do is take, let's say, 3 times the first row of one matrix and add it to the second row of another matrix, and replace that, replace either of the rows with that expression. So I could take some sort of linear combination of rows, and we're going to practice that in another video. Okay? Before we do that, though, I do want to make this one comment. I call this a boring comment on notation. I'm not going to be very careful in my vocabulary with this. I don't really see the need to. But our goal, when we're working with a matrix, in this case, say we've got matrix B here, or we've got maybe this system of equations over here, and we've written it as a matrix. Our goal is to be able to easily obtain the solutions, and we do that by putting the matrix in a certain form. So generally what we'll do is we will put the matrix in what's called reduced row echelon form. I'll abbreviate that as RREF, and it's also sometimes called diagonal form. Notice that here I have what's called a pivot 1 here, and below that pivot 1 I have all zeros. And then I've got another pivot 1 here. I'm going to explain that more in subsequent videos, but above and below that pivot 1 I've got all zeros. Likewise, here's a pivot 1, and above all of these, above and below, but there is no below, I have all zeros. So when that occurs, we're going to say that we are in reduced row echelon form. And the reason why we like to do that is once we've taken whatever the original matrix A was and put it into RREF form, we can just simply rewrite this now as its as its corresponding system, and then read the solutions that way. So this corresponds to the z variable, and it says this is just the very simple equation z equals r. And this corresponds to the y variable, so it's 0x plus 1y plus 0z equals q, or really just the equation y equals q, and here we can just read it off as x equals p. So this is the solution to this system, and we can actually read it right off when we are in this reduced row echelon form. Okay. One thing to note here is this is a square matrix, meaning we've got to the left of the augmentation bar we've got 3 rows with 3 columns, and this will not always be the case. So reduced row echelon form won't always look quite so nice, but again, the issue is we've got these pivot 1s and we've got zeros above and below those pivot 1s. I'll talk about that more in subsequent videos. Okay. So text will sometimes say, put your answer in reduced row echelon form, put your answer in row echelon form. I'm not going to worry about that so much. Usually it'll be helpful to put it all the way down into the reduced row echelon form in order to read solutions, but notice that if I just put it into what I call row echelon form, look at the difference here. This is reduced row echelon form, and it's got the zeros above the pivot 1s. If I just put it into row echelon form, where all I'm concerned about is getting zeros below the pivot 1s, I can still pretty quickly find the solutions. Notice that I can immediately see that z is equal to r in this, and then I can back substitute. Let's say r was 5. Then I could plug in a 5 for a z here, and I can immediately, just by moving this term over, solve the system for y. And then now I know that what z is and what y is, I can quickly solve for x just by doing some simple addition and subtraction. So reduced row echelon form is sort of taking this procedure that we're going to teach to its conclusion, but sometimes we might just stop at row echelon form. I'm not going to worry too much about, when I ask you to give me the solutions to a system, whether you put it in reduced row echelon form or just row echelon form. That's sort of your preference, but I wanted to make that comment on notation. All right, this was a fairly lengthy video. In the next one, we're going to actually go ahead and solve a system of equations by row reducing the matrix. And we're going to see what I mean by that there.